Okay, today we're gonna, complete or not complete, continue with RRT, rapidly exploring random trees. Okay, so this is the last examples we saw. You guys can see my screen, and
Yes.
we played with some of the parameters of that algorithm, like the goal node location, for example. The maximum connection length or the range around the new node, and the number of segments. Okay, and we saw what each one of those kind of how each one of those can affect your final result. So for example, if you hide the goal somewhere not easily reachable, then you will probably end up with many nodes. So for example, here more than 300 nodes versus 127 nodes in before. Okay, with a more reachable goal location. If you change the connect length to 50, then you are forcing the algorithm to create a tree in which the nodes are very close to each other within 50 meters, for example. That's why we have here, you know, more than 5,000 nodes before reaching the goal. Okay. And here is the effect of the number of segments. If you decrease them, of course, if you increase them too much, you will process more, you will make more processing, but you are very conservative. So you will end up with a true or valid map, a map that has no crossing like this. You see guys the crossing here. But if you have very small segments, yes, you will not do a lot of calculations when you are determining if there is an obstacle or not between two nodes, but you may end up with something like this, all these violations. Some of them they are not dangerous, like those, for example, because they are not on the path from the goal to start. But these two here are on the path from the start to goal. So, for example, the start here, this is the starting point of the robot. He will move like this in the map, and he will just stuck here. He will not be able to continue because he will hit a wall like this. Okay. Okay. Now we're gonna improve RRT, and there are ways to improve it. And when I say improve, usually we will increase the amount of computation, and that's what exactly we're gonna do. So we're gonna increase a little bit the amount of computations in order to get more or shorter paths or more optimal solutions or near optimal solutions, we can say. Okay. So basically, we're gonna do two steps, and by the way, they are independent. I mean, you can apply. They are dependent. Yeah, the wiring is dependent on the second step. It's called wiring. It's dependent on the first step. It's called the choice of the parent. They are dependent on each other. But I mean, you can apply the first step, but and just don't apply the second step. Okay, but if you want to apply the second step, you must apply the first step. Okay, so and both can give you some boost or near optimal solutions in the shortest path between the goal and the start node. So for example, the choice of the parent. So in normal RRT, okay, when you have a range for any new node, like for example, you know 100 meter, you were searching around the node for the closest node. For example, if within the range there are two close nodes to the new node, for example, one uh, 50 meters away and another one is 60 meters away, then you will connect to the 50 meters away. This is what we were doing so far in RRT. The choice of the parent can affect the shortest path or the near optimal choice, or can improve the distance between improve mean decrease the distance between the goal and the start. So let's see an example here. Here is the new node, okay, and here is the range between, and within that range I will search for neighbors or parents to connect it to. We have two nodes within that range, okay. In RRT we choose the node, the closest one, and connect to it. In that case it's B, not B, because it's just 1 meter away. So if this is RRT, normal RRT, I will connect the new node to B. In RRT-star, which is the name of this improved RRT, no, we choose one of the short, we choose the node that has the shortest path to or distance to the start node. Okay, so for example here we have again two nodes. Okay, node A is 8 meters away from the start and 10 meters away from the new node. So that the total distance from the new node to the start, if we choose A, is 18 meters, because I will move like this, then like this. B is 12 plus 9 meters away from the start, which is 21 meters. So if I connect to B, so there will be no, this edge will not be there. So I will connect to B. So I will consume 1 meter, 13, 22 meters to reach the goal. Also, if I connect to A and I want to go to the start node, I will move 10, then 8, totally 18 meters. Okay? So it's better to connect to A rather than B. Okay? Now, this is clear, guys? This step is clear because it's important to understand this. So this will be the final graph. These three black edges and this green edge. This red dotted edge will not be there because this is an RRT. In RRT, we gotta connect the new node to B, not to A. So we will not have this edge, but we will have this edge. But we will have a longer path to the start node. With RRT-star, with this step here, we're gonna connect it to A rather than B. So this will be the final graph. And this will be not there, this edge. The second step is called rewiring. Okay? What we're gonna do in this rewiring? So again, with the same range, okay? Now our new node is connected to A, that's good. Now we're gonna check other nodes if they can connect to the new node and reach the start node faster or shorter, with shorter passes, shorter distances. So let's see that. In the beginning, B was connected to start using this node. And the total distance was 12 plus 9. Also, if the parent of B is a new node, it will consume 1, 11, 19 meters, not 21 meters. So it's better for B to connect to the new node as a parent. So the parent, previously the parent of node B was that node. Now, after the second step, the rewiring step, the parent of B is the new node. And we will remove this edge from the graph or the tree. And this will be the final shape. You have this black edge, green edge, another green edge. And you will not have this edge. Okay? So let's do that on the tablet as an array. And let's see how it's gonna, how the program will behave. You guys can see the tablet?
Yes, we can.
Okay. So let's say that we have here the start node. We have this guy, and this guy. So this was the array in which we represent the tree we have before creating the new node. Now we create the new node, and it's valid, it's away from obstacles, and you want to connect it to a parent. RRT will just measure the distance. So we have, for example, some distance around. This will be bad drawing. So for example, this is just forgive me for this, it's not that good. So let's assume this is the range, the 100-meter range, okay, which we use it to assume. This is the maximum distance to connect. So within this maximum distance, we have two nodes, A and B. This is 1 meter away, and this is 10 meters away. RRT, again, will choose B. So with RRT, we're gonna add the new node. Let's call it new node. And its parent will be B. This is RRT. Normal RRT. RRT star will not do that. We'll do something else. So new node. So here 1 meter plus 12 plus 9. This is 22 meters. So if the new node chooses B as a parent, and we want to go from start to the new node, we're going to move like this, 9, 12, 1, which is 22. If the new node chooses A as a parent, the distance will be different. It will be 10 plus 8, which is 18 meters. So RRT will choose A. So this will be the final graph. And we're going to add the new node with the parent A. Okay. Now, another step that RRT adding, which is rewiring. So after putting this or assigning this parent, we're gonna check now the nodes within the range of the new node. If they got, based on this new node, if they got better route to the start or shorter route to the start. B currently has a parent of C. And if we want to move from the start to B, we're going to consume 9. The distance is 9 plus 12, which is 21. Also, if B has a parent equal to the, if the parent of B is a new node, and the distance is this distance is 1 meter, and we're gonna reach B from start through the new node, we're gonna consume 8 plus 10, 18 plus 1, which is 19. I'm sorry, yeah, 19. So in the beginning B was 21 meters away from the start node. If it has a if its parent is C. If it will be connected to new node as a parent, I mean we change this to new node, then we're gonna reach node B from the start. We're gonna consume 8 plus 10, 18 plus 1, 19, not 21. So it's better for B to connect to the new node as a parent. So we're gonna update this node to the new node. We're gonna change this location in the array and put the ID of our new node. And of course, if we did this, then it's like we removed the edge between B and C. Okay, and this will be the new graph now, which is a better graph or a better tree. And the final, after adding this node, the final graph, the final array will be like this: S infinity, which means it has new parent or the root of the tree. C, its parent is S. A, its parent is S start, and B, its parent is the new node, whatever you call it. And the new node has a parent of A. This is clear, guys? Any questions?
Wait, why did it replace the C with new node? I wasn't too sure why that happened.
Okay. So let's bring it back. Okay, let's and remove this. Okay, now if I want to go from start to B, what is the cost from start to B? I should go from start to C, then from start to B. Here is the distance is 9 meters. Here is the distance is 12 meters. Then the total distance is
21
meters. Okay, good. Now let's assume this edge is not there. And the parent of B is actually the new node. So let's now calculate the new distance from S again to B, but through this node. So we're gonna move from S to A, from A to new node, and from new node to B. This is 8, this is 10, and this is 1 meters. So total is 8 plus 10 plus 1 is 19 meters, less than 21 meters. So it's better for B to have its parent as a new node than as C. That's why we remove the old, we updated, we remove the old, because we discovered that we can reach after adding the new node, we discovered that we can reach node B using a better route. You got it?
Yeah, I see it.
Good. Any other question, guys? Okay. So let's see the effect of the, let's go back to the, okay. Here is a comparison before and after. So this is normal RRT, okay? And the distance, if we added up the distances between these nodes until we reach the goal. So this is the start, and this is the goal. The distance is 2,300, okay? And we see clearly it's really bad. Because if you want to reach, you have something, you have to, for example, move like this. Oops. So here you have the route, goes a little bit to the left, or the left, then go down, go right again. If, for example, here we can connect these two edges together, it will be much better. Okay, but it's good that this is happens too fast. The RRT is really rapid exploring random tree. Okay, so you can find the path between the start and the goal in very quickly. Now, if we apply only the step one, only the step one, which is connecting to, so if you discover a new node and you want to connect it to some parent, you choose the parent that will lead to the start node with a shorter path. If we apply this only without rewiring, then look at the path. The path similar, okay, but here you see this area here. This area has enhanced, has improved a little bit. So if we just tell yourself, if we just move like this from here to here without going down, then up again, then right, it will be better. And the total distance now is 1990. It is around 400 difference, 400 meters difference. Okay. And now, after applying both steps, which gives us the RRT-star, and look now how the route become much much finer, much shorter. Okay, and it's now 1589. Okay, you guys are convinced with this? You see it? You understand that? So let's go to the coding. Okay, although it's really simple to explain, but in the coding it's not that simple. Yeah, this is the stuff. So let's go again very quickly on the RRT. It's just RRT, but I added just two new sections. That's what I have done. Just adding two sections. Same code exactly, with just two sections that I will show you now. So again, we have, this is the map, 1300 by 1300. This is the obstacles in the map. I added just one. So yeah, I have added this wall here. This wall and this wall. There were not if you go back to the previous map, no, it's not here. So this in BRM, this place here, these edges were not there, but I added them to RRT just to change the goal location and see what's gonna happen. Okay. Okay, these are the obstacles. Okay. Maximum connected links 200, segments is 100. Again, this variable that says if I found the goal or not. And we don't need this. Okay. And here is a Boolean variable called rewiring. If I want to add the second step, okay, I will make this true. If I don't want to do the second step, okay, I will just make it false. So we have step one, in which the new node is connected to the node that will it will create faster route or shorter route to the start node. The second stage is called rewiring, which is you have the option to do it or not. Okay, so this Boolean variable here, say if I want to do that or not, second stage or not. Nodes again is just a counter for the number of nodes in the map. Okay, here is I'm creating the map with the obstacles that I created previously. Here is the graph array, the tree array. is the start location. I am adding here the start location to the tree. But there is another step that we should add, which is the distance to start. So now the array will be 3 columns, not just 2 columns. So let me do that very quick on the tablet to show you what I mean exactly by this. So this is the old array. It's only 2 columns. I'm gonna add a new column for it, which is distance to start. Of course, the start node has a 0 distance to start. It's the same location. C here has 9 meters to start. A is 8 meters. B, yeah, B now, since it's connected to the new node, it's 19 meters. And the new node, it's 18 meters. Because I'm gonna use this when I compare between the many nodes that I can connect to. So I will connect to the one that will lead me or create a faster route to the start node. Okay. Okay, here I am marking this location, the start location, as a node, and a node in the map has 2. And drawing the start node location, then defining the goal and draw it on the map, then the while loop.
We can't see the MATLAB.
Yeah, of course. Now?
Yeah.
Okay. So I just, we stopped here. So this is, the ID of the start node. This is defining its parent. It has no parent. So I just give some, some symbol for that, which is infinity. And 0 is distance to start node. Of course, the distance to start node from the start node is just 0. Okay. Then in the map, any point that I choose in the map and put in the graph, I mark it by 2. So the start node is just our first node in the map, on the tree. Okay. Here I am plotting the start node. Here I am defining the goal node and plotting it. Then the while loop. First generate just random node with random, x coordinate and y coordinate. If it's an obstacle, just go back and generate a new one. Or if it is, generated before, then also go and generate a new one. Here I am searching for the nodes around the new node within the range, which is 200 meters. And I will put all these nodes in this neighbor distances. Okay. So I will loop over all the nodes currently in the tree. For any node, I will get its row and column coordinate. Okay. If the distance between the new node and this node is larger than the range, the maximum connection length, then I will just continue and get a new node. This node is not valid for us. If it's within the range, Then I will check if there is a gap between, or an obstacle, I'm sorry, between the new node and this neighbor. If there is, then go back and generate a new one. If there is no gap, if there is no obstacle between the node and the new node and the neighbor, or this neighbor, then I will add it to the neighbor distances, okay, which is just an array that has the neighbor ID, the neighbors that I can connect to, and the distance to that neighbor, which is the norm. Okay, square root of x minus x square plus y minus y square. Now this is the first improvement over RRT, which is how to choose the parent. Okay, all the parent, the candidate parent, we can say, are in this neighbor distances. Okay, so I'm just getting it and sort it. By the way, you can just skip the sorting step, and you can just go with the neighbor distances, because we don't need now to connect to the shortest distance. I will not choose the one that is closest to the new node. I will choose the one that has shorter distance to the start node. Okay, but you can just add it, that's fine. So I will mark this node, the new node that is covered, and increment the counter, because I discovered, since I go into that in that part of the code, that means the new node that I discover is a valid node, and it can be connected to one of its neighbors. And I upload this node here. Then I will loop over all the neighbors that I can connect to, or the new node can connect to. Okay. First, I'm getting the row and column of this of the neighbor. It check the distance from this neighbor to the new node. Okay. Then I will get the distance from that neighbor to the start node, which is located in the tree connections array, the third element of that row in which this neighbor is located. Okay. The total distance between the new node and the start node, if I'm going to connect to that neighbor, will be the distance between the new node and the neighbor, and the distance of the neighbor to the start node. Okay. Since I am concerned with the minimum, I will connect to the one that will give me minimum distance or minimum route or optimal route or shorter route to the start node. Okay, I made this comparison here. So we have here a variable. This variable equal to infinity in the beginning, but then it will be resetted to the minimum value, the minimum distance to the start node. It's like searching for the minimum. Okay, you start from very big value, and if you find a smaller value, you update this variable called minimum distance to start, and so on, until you find the minimum one. Okay, so if the current distance is less than minimum distance to start, then I will update this value, because we found a closer neighbor to the start, we can say. So we will update this variable to this distance, okay, and assign this neighbor as my parent, or the neighbor to connect, okay, and I will store the row and the column of that neighbor that I'm going to connect to, because I'm going to use this row and the column afterwards, as we will see. And here is the distance from the new node to the start node if I am gonna use this neighbor as a parent. Okay. When this loop is finished, when I loop over all the elements inside distance array, distance is sorted array, that means I get the ID of the neighbor that will give me the shortest route to the start node. Okay. So I will add this information and the new node to the graph array, the tree array. So tree array equal to the previous tree array, and put a new row to it, and this row will have the ID of the new node, the parent, and its distance to the start node through that parent, of course. Okay. And then draw an edge between the start, between the parent and this new node. Okay, so let's make this is then the wiring step. So I will make the wiring step false, so I will not do it, and let's see how the tree will evolve. Okay, this is the first node. I connect it to the start and generate a new one. Look here, this is very interesting. So look, this node, when I generate it, we connect it to the start node directly. If this is just the normal RRT, it will be connected to this one, because the distance between this node and this node is less than the distance between this node and the start. But if I connect this new node to this node, this old node, the distance to the start will be larger or greater, because I am gonna move like this, from this to this, then from here to the start. But now I can go directly to the start node. Okay. Look now at this node. This node, if this is RRT, normal RRT, it would be connected to that node, because it is the closest one. But now with RRT-star, the first improvement, I'm gonna connect to the start node directly. Just watch that. Okay. And so on. I have a lot of nodes, but we're almost there. Yes. Okay. You guys got that? Okay, let's now go to the rewiring step. This is the rewiring. Okay, since it's true now, we're gonna do that. Okay, so all the nodes around the new node are already located or stored in that array, neighbor distances, or even distance sorted, because distance sorted just the neighbor distances array but sorted. Okay. First, of course, I will not do any rewiring if if there is, just one node in the neighbor distances. There should be at least two nodes, like the example that I explained here. There were two nodes, A and B. This is the minimum condition. So I will not do the rewiring if I have one node. Okay. If I have two or more, then within the range, then I can do this rewiring. Okay, so let's see. What's gonna happen now is that I will compare for any node in the range of the new node. I will compare its current distance to the start and its distance to the start if I connect it to the new node as a parent. This is what we're gonna do. So first, let's get the distance to the start of the new node of the current neighbor. We can say neighbor I, or the neighbor. So the new node distance to the start is equal to now nodes is equal to the number of nodes that we discovered so far, and the last it points to the last row in the tree connections graph. Okay, so the last row now in the tree connections graph, this array is the new node, its parent, and its distance to the start in the third place. So that's why the new node distance to start is equal to three connections of node and 3. Okay. Now I'm going to loop over all the nodes in this array. So first I'm getting the distance of that node to the start. Here I am, naming the variables very long to make it more descriptive. So neighbor I index in tree. So this is first the index of the ID of that node. So just to find it, I'm just finding it in the tree connections first column node, first column. Then I'm getting its distance to the start, and then I will compare the two distances. Okay. The distance to the new node is equal to norm of its the new node y, the new node x, and the current neighbor row and the column. And the distance to the start through the new node is equal to the distance to the new node plus the new node distance to the start, this value. Then I'm gonna compare this one, this variable, with this variable. If the distance to the start to the new node is less than, then we're gonna update its parent. It's better for this neighbor to be connected to the new node as a parent. Okay. So since in here, whenever we connect to a parent, we make an edge. So we need to omit this edge from the graph, from the plot. So that's why first I'm getting the parent row and column, the old parent. Okay, that I'm gonna update now. And this is the ID of the new node. Yeah, then I'm gonna update now the parent of this neighbor to the new node ID. And update the distance of this neighbor, update its distance to the start node. So this location of the neighbor, location number 3, with the new node distance of start through new node distance. Then I am plotting an edge between the new node, which will be the parent now of this neighbor, and the new this neighbor. And then here I am removing the old edge between that neighbor and its old parent. And how can I do that? I'm just drawing the same edge again, but it was white. So it will be matched to the background, so it will disappear. Okay? So any edge here is in blue. If you draw an edge here with white, it will disappear. Okay? Then the rest is just the same as RRA. The rest is that I'm checking if I'm close enough to the goal. If I'm close enough to the goal, then I will add the goal to the tree and connect it to the new node and draw or construct the path to the start. Here I'm constructing the path using this. This is your homework. Okay, and here I'm drawing this path in green. Okay, so let's do step by step. So let's add some. Yeah, let's do one here and one here. Let's see. Okay. Till now, just normal. Till now, normal. Normal, I mean the rewiring is not taking place. Yeah, now there is a rewiring. Okay, so let's see what's gonna happen. Just look at the graph because one of the edges will be white now. Yeah, and then I will remove one of the edges now. Yes, you see that guys? So this node here was connected previously to this node. Okay, then we generated this new node here, and this node discovered that if it's connected to this new node, it will have a shorter route to the goal location, to the start location. Okay, so the previous edge was removed and a new edge is created between that node and that node. This is clear, guys, or let's continue to see other examples. Yeah, now there will be now another new edge. So let's go step by step. Yes. So again, this one was connected to that one as a parent, but it found a new shorter route through this new node to the start location. So we removed that edge. There was an edge here that we removed, and where is the new edge, which is this one. So let's continue. Yeah. Now we have another example. So let's see what's gonna happen. Okay, so we're gonna draw a new edge now. Good. So this node now previously was connected to this node. Now there is a new route, a shorter route to the start through that node. So we connect to that node now, and we will remove this edge. Okay. Let's continue. We have other examples. Yeah. And again, this node was connected previously to this, and now it finds the shorter route to the bus through this node. So, okay. And another example, maybe not that clear. Okay, you got the idea, guys, or is there anything not clear here?
It was
Yes.
pretty hard to digest. I just don't know how like it chooses like the new one.
Step 2, right? Rewiring.
Yeah, I think that's where I'm getting kind of confused.
So let's keep the program. I mean, so let's stop this, and before going to the tablet, let's do it again, but from the beginning. So let me. Okay. Till now, nothing new, nothing new, nothing new, nothing new. Yeah. Now, look now. This node, okay, this node here, okay, is connected currently to this node, then the start. So if I want to move from this node to the start, I should move like this, then this. Through this edge, then this edge. Okay? But turns out, if this node was connected to that node, which is a new node now, currently, this is in the Matlab coding now, I mean, the Matlab program now, this is a new node. Okay? So this node, it's better for it to connect it to that node rather than this one. So we will connect it to that one. So let me continue. We're gonna draw an edge between that node and that new node. And then because a node should have only one parent, so we must remove the old edge. Okay, we mark it with white. That's it. So we're gonna continue. We're gonna remove now this edge, or I'm saying that this node will no longer be connected to that node. Is that okay?
And that process there, it's checking like neighbors within a certain radius around it, right? And
yes.
Let's
do it again on the tablet. You see the tablet, right?
Yes.
I'm gonna draw something similar to what in the. So we have the start. Okay. It's connected to some node here. And some nodes there. Okay, this is the original graph. Let's assume this is the original graph. Okay. and this is, for example, 100, and this is 200. Then we generated a new node. Okay. And we are searching around it in some radius. So let's assume the radius is big. So any node within that circle can be a parent for that one. But we will choose the one that will lead us faster or shorter to the start node. This is the start node. This is node A, for example, this is node B. Okay? Let's take them one by one. So the distance, let's assume it's also 100. So if we take start as our, parent, the distance will be 100 if the parent equal to start. If the parent equal to A, let's assume this is 70, then the distance it will be 170, because I should move like this, then like this. If the distance is B, let's assume this is 180, for example. The distance even will be bigger, 180 plus 200 plus 100, which is 480. So what will be the parent based on that analysis for the new node? It will be the start. So we're going to choose the start node as our parent. This is the first step. Okay, so now we have the graph is like this. So the parent of A is the start, the parent of B is A, and distance is 200 plus 100 is 300. And here is the new node, let's call it N. N will have a parent of start and the distance is 100. The rewiring. Any point within the range will check if the new node is better for it to be a parent or not. Will lead it faster to the goal or not, the start or not. So let's start by node A. Node A now currently has a start node as a parent. If node A has a parent of the new node, the distance to start will be 70 plus 100, 170. But now it has only 100. So we will not change the parent of A. How about B? If the parent of B is new node, then the distance to start will be 180 plus 100 equal to 280. With the current parent B, C current, which is A, the distance is 200 plus 100, it's 300. So which better for B? To take A as to keep A as parent, or to update it to, or take a new parent as N?
Well, 280 is better than 300.
Yes. So what's gonna happen is that B will take N as a new parent. and this sense will be changed. So this node will be removed, and this will be the final graph.
So in this case, we're making the parents of each of the nodes equal to the new node. That's how you wrote it right there. The parent of A is equal to new node, and parent of B is
No,
equal to.
no, yeah, this one, yeah, I am checking if A now has a parent of S. Okay, if A takes N as a new as a parent, okay, and wanna move from A to S to the start, we're gonna move 70 plus 100.
Oh,
But
okay.
now A can go to S with only 100. So it's better not to take the new node as a parent. But for B, it's better. For B, it's better to take the new node as a parent rather than A. Okay? Because now, if I'm gonna move from B to S or from S to B, the distance will be 280, not 300. Okay?
So we're basically comparing like the distances, uh, right? The distance to start on the left-hand side where you have the 0, 100, 300, 100 with the distances that you get when you set the parents equal to the new node.
Yes, yes. You compare and you take the minimum. If you
Oh,
discover that the new node will be shorter route, to any of the nodes, then you change the current pair of these nodes to the new node n.
okay. I think I get it more.
Okay, just to read the code, you know look at the lecture, try to think yourself, if I'm gonna write this code, what I'm gonna happen, what I'm gonna write, or how gonna code this, and you will understand better the code itself. Okay. So let's do a couple of more steps. So in our map here,
We can't see the MATLAB
yeah,
screen.
okay. So now, for example, again, this or this node, one of these nodes, will be better to connect through that node to reach the goal. Let's see. I think that node. We're gonna see now. Oh, that node. Okay, that's fine. So we're gonna remove this edge and keep the shorter one. Okay. And create another one. Yeah, and even this, both of them has changed their parents. This is interesting. Yes, should remove this. And you can continue, you know. Of course, marking all the edges with white is not a perfect idea because you may have something like this. There is an edge here, but because there are many, you know, white edges crossing, so it's not that clear. Okay. And you continue. I just want to reach some point at which I'm gonna show you that this, you know, this complication here will be removed, so we can reach the goal faster. I'm not sure when exactly it's gonna happen. Actually, it happened. Yeah. So some you know, some point we just missed. There was an edge between that point and that point, but this edge was removed so that we took a shorter route to the start. In the beginning, we were moving something like this, which is really, you know, longer path than this one. Okay. You guys got the idea?
Yeah.
Okay. Okay, that's it for today. I published, by the way, a homework. It's RRT homework. Okay.